So the unofficial title for this is trying to find a mathematical home for our classical phenomenon. Phenomenon is a word that I invented to describe everything we see around us. And Sidney Harris, the cartoonist of science, aptly captures it when he has a bunch of cosmologists sitting around and saying, if we run our picture of the universe backward for several billion years, we get something resembling Donald Duck. We must have made some kind of mistake. Because that is, when you try to ask the biggest questions, you get the biggest, as I understand from what little I know about cosmology, you get the biggest confusions. You should be used to that. So I think we need to understand some of these things so that there are many different intended to consider a reasonable model. Should a model in some sense be reversible? What does reversible even mean? It generates enough complexity in a non-paradoxical way the world we find ourselves in. So the kind of discipline areas of expertise we need. How many people here are order? Okay, how about general relativity? Quantum field theory? Okay, good, we have something. And how about actual cosmologies like the ordinary Big Bang and the inflation and eternal inflation ideas? Okay, we got some people who know about that. Okay, wonderful. What about fault-tolerant computation and topological stabilization of computation? Oh, good, good, all right. Decoherence theory and emergence of classicality? All right, good. Okay, so how many people knows about all of this stuff? All right, so that's what we're here for.
In a few days we will.
Or we'll not know about some parts that we thought we did know about. So here's my simple classical model of a system that's sort of physical, except it's discrete and classical and not quantum. So it lacks a lot of the things we'd want for a real cosmology. And it's a energy conserving deterministic reversible cellular automaton. So it's sort of like a discrete version of Newton's laws of motion. And you can start it in a very simple state, which is periodic. Time goes this way. With just a little defect in the initial condition, you get this deterministic complicated pattern. It gets bigger and bigger and more complicated as time goes on. And the rule is very simple. It's a deterministic Ising model. The center site is not used, but the future of it is equal to the past, XORed with the condition of there being two of the four nearest neighbors, white and two black. So that's a second order discrete dynamical law that's a kind of a toy model of Newton's equations. So my favorite kind of complexity involves space-time complexity and also program size complexity or Kolmogorov complexity. And it's a computerized Occam's razor. So let's look at Occam's razor, where we're trying to explain a phenomenon and we want to choose the most economical hypothesis. And our choice of economy of hypotheses is done without regard to the length of the computational path that goes from the hypothesis to the thing it explains. And now we want to say, well, the problem is that how do you measure the economy of hypotheses? Usually Occam's razor is used by scientists to argue that their own hypothesis is simpler than everybody else's, and therefore that it shouldn't be changed. But we can, of course, like everything else in this world now, we computerize it, digitize it, so the alternative hypotheses are bit strings. The rules of inference are a standard universal computer, and the object has been digitized that we're trying to explain. And so the Kolmogorov complexity of the object is the size of the smallest program. And the thing that we're interested in is not the size of it, but the running time of it. And we smooth it out a little bit to take account of programs that are near minimal in size. So the idea is this object it contains internal evidence of having been the result of a long computation. And looking at this toy model and waving your hands and shoving under the table things like the P equals P space question, we can say that the logical depth of this thing increases for a while, because if you take a slice of it here, the whole slice, or even any reasonable sized part of it, contains internal evidence of that evolution that produced it. But if you let it run for a long time, exponential in the width of the system, it goes to this kind of equilibrium state. And of course, it's the result of a very long computation, but it doesn't really contain plausible evidence of that computation, because in order to describe that history, you have to say how many steps you had to run it from the beginning, and that number itself is of order the number of bits in the system. So the thing gets complex by one process of having evidence for a longer and longer history, and then it loses its complexity as it equilibrates by the plausibility of that true hypothesis becoming unpersuasive compared to alternative hypotheses, like it just happened in this state. So I just said that. So this is a toy model, but I think the real world is sort of like that. If you take our world and allow it to equilibrate by, say, putting a mirror ball around it, eventually it'll just go to a thermal state.
You're never running the thing in a time exponentially in the size of the universe.
No, but a finite system, you would run it in size of that's a very good question. Like, does this way of thinking apply to infinite systems?
Or even just big enough?
Big enough. Well, I'm going to care about very long times here. Okay. And whether you should care about them is something we should discuss. Anyway, so, okay, that's all I have to say about that.